Hi, welcome back to ACE Physics. Today we are going to be looking at particles and the standard model. What we're going to do is we're going to create one sheet here with all the information we need to then go and answer some exam style questions on the topic. And that's our aim at A-level. Our aim is to look at all the information we need and try and condense it onto ideally 1 page per topic or maybe 2 pages per topic. So here we're going to get everything we need to know about particles and the standard model on this one sheet. So what is particles? Well, we knew at GCSE and also at the start of the 20th century that we had protons, neutrons and electrons, and they made up all elements, everything we could see in the universe basically. So we were happy. But then scientists started looking in the 1950s at particles coming from outer space, what we call cosmic rays. And these had an abundance of other particles in them. So scientists didn't like this. So the first thing they did was they classified these particles into 2 groups. So we had leptons and we had hadrons. Okay. And in order to explain all these particles, we had to come up with another particle that actually made up one of these groups. So leptons are fundamental. So they are fundamental particles. They are not made up of anything else. They are fundamental. Hadrons, however, are made of quarks. So this other particle that we theorized at the time, we've now proven they exist, made up all of our hadrons. And our hadrons were also split into 2 groups. We had baryons, which are made up of 3 quarks, and we had our mesons, which are a quark and an antiquark pair. So while I mention antiquarks, it's worth mentioning that for every particle we have, there is a corresponding antiparticle. Now, the antiparticle has exactly the same mass, but opposite quantum numbers. And we'll look at quantum numbers in more detail now. So let's look at the particles we need to know in these categories. So leptons, we have electrons and we have muons. Muon is essentially a heavy electron. It's got a higher mass. Give it a mu symbol and a minus. And each one of these has a corresponding neutrino. So we have the electron neutrino, and neutrinos are given this symbol, and we have a muon neutrino. And again, that will be given that symbol with a mu. Baryons, the only 2 we need to worry about really at A level are a proton and a neutron. We'll say proton, we don't need protons. Okay, and mesons, we've got pions. We have a pi plus, we have a pi minus, and we have a pi 0. And we've got kaons, which we have a K plus, a K minus, and a K 0. Now, there are others, mesons, there are other baryons, but we don't really need to know too much about them. So we've got these things called quarks, which we mentioned. You're given this in your data booklet, but it's worth having here. We've got an up quark, which we give a U. We have a down quark, which we give a D. And we have a strange quark, which is an S. So a proton is made up of 1 up, and 1 down quark. A neutron is made of 1 up and 2 down quarks. And we can kind of figure this out because what we do is we have all the quarks have a charge, which is a fraction of the charge of a proton. So an up quark has a plus 2/3 E charge. A down quark has a minus 1/3 E charge. And a strange is a minus 1/3 E as well. Quarks also have this other thing called baryon number. They also have a baryon number. And the baryon number is 1/3 for an up quark, 1/3 for a down quark, or 1/3 for a strange quark, which means a baryon, because it's got 3 quarks, will have a baryon number of 1. So baryon number would equal 1. For a meson, though, it's a quark and an antiquark. So the antiquark has the opposite quantum numbers. So it would have minus 1/3 baryon number. So the baryon number of a meson would be 0, which kind of seems obvious because it's not a baryon. Same with a lepton, would have a baryon number of 0 because it's not a baryon. They also have this other strange property called strangeness, and only the strange quark has a strangeness, and the strange quark has a strangeness of -1. So those numbers are important. We have some other numbers that come up. We have a thing called lepton number. So any lepton has a lepton number equal to 1. Obviously, a meson has a lepton number of 0, and a baryon has a lepton number of 0, because they're not leptons. So only a lepton has a lepton number. Our other quantum numbers are our strangeness and charge. So we've got charge, baryon number, strangeness, lepton number. They are our 4 quantum numbers, and they must be conserved in all interactions, apart from strangeness. We'll look at that in a little bit more detail as well. The last thing to look at is our fundamental forces. So we've got 4 fundamental forces, and each one of those forces has an exchange particle. An exchange particle is the particle that carries that force between 2 things. Okay, so if things are going to interact with each other, something needs to be exchanged between them. And what that thing is what we call an exchange particle, sometimes also known as a gauge boson. So we've got 4 fundamental forces. The first one is the strong force, or the strong nuclear force, and that is mediated inside a proton. The strong force holds the quarks together, and the exchange particle for that is gluons. In a nucleus, which is normally where we look at it at A level, it holds the protons and neutrons together. It has to be stronger than the force pushing them apart, and the exchange particle is virtual pions. Again, that could be a pi plus, a pi minus, or a pi 0. We then have the weak force, which generally is responsible for particles splitting up, so particles decaying. And the exchange particle for that is a weak boson, which is a W plus, a W minus, or a W0. We then have the electromagnetic force, and the exchange particle for that is virtual photons. And then we have gravity, and the exchange particle for that is the graviton. Okay, weak force is important because strangeness must be conserved apart from in weak decays, where it can change by plus or minus 1. So I'm just going to make a little note somewhere on here just to point out that all quantum numbers, quantum numbers must be conserved, but strangeness can change by plus or minus 1 in a weak decays, Okay, so that's kind of a little aside to that. But that's everything we need to know about particles right there. This is important because sometimes we need to use this information to figure out the quark structure of something, as we will in a second. All the quantum numbers are important, and all of our exchange particles are important. One other thing to mention is that another way we can distinguish between our leptons and our hadrons is the hadrons experience the strong force, and leptons do not experience the strong force. So the strong force doesn't work on leptons. So they're fundamental and they don't experience the strong force. Whereas hadrons are not fundamental, they're made up of other things, but they experience the strong force. I would say the fact they do and don't experience the strong force is the best way to differentiate between them. But you can also say that hadrons are made of quarks and leptons are fundamental. Okay, so let's look at some questions. And it's the fact they don't experience the strong force is important when we're looking at decays, because if we have just hadrons, could be the strong force or the weak force. If we've got hadrons and leptons, must be the weak force that is mediating that interaction. So if we've got hadrons and leptons, because we know it's a weak force, so it could be a weak decay, that means strangeness comes into play and could change by plus or minus 1. So let's look at some questions. So the questions you'll get are, here's this interaction, is it possible? And the way we do that is looking at our quantum numbers. So we've got baryon number, we've got charge, we've got lepton number, we've got strangeness. So we look at each one. So baryon number of proton, it's a baryon, so 1. Pion is a meson, so 0. That goes to a kaon, which is a meson, plus a pion, which is a meson. So that is not allowed. So I now don't need to look at the rest, because I know this is not allowed, as baryon number is not conserved. And this is how I would lay it out. I would lay it out like this. Let's look at charge anyway. We'd have 1 plus minus 1 goes to minus 1 plus 1, so that would have been okay. Lepton number is 0 plus 0 goes to 0 plus 0, so that would have been okay. Strangeness again would have been 0 to zeros, so that would have been okay. But it doesn't matter, because baryon number wasn't conserved. Okay, let's look at the next one. Is this allowed? Well, we'll do the same thing again. We're going to look at baryon number, charge, lepton number, and strangeness. So we've got a baryon number of 1. A electron antineutrino is a baryon number of 0, because it's a lepton. Neutron is a baryon number of 1. Positron, baryon number of 0. This is a lepton. Okay, charge. We've got 1 plus 0 goes to 0 plus 1. So we can see 1 on that side, 1 on that side, 1 on that side, 1 on that side. Both those are allowed. Lepton number, 0 minus 1, because the anti-electron neutrino is minus 1. So an antiparticle. Neutron 0, plus or minus 1 there as well. So we'll put plus minus 1 like that again here. So again, that would be allowed. And strangeness, None of them are strange. So there we go. One thing about strangeness, you'll always be told if it's strange, if the particle is strange, other than a kaon. So kaons are strange. So our kaons are our strange particles. We know kaons are strange. Anyway, to the slight aside. Again, is this allowed? Well, we've got baryon number, charge, lepton number, strangeness, pion, not a baryon. Goes to not a baryon, not a baryon, not a baryon. So that's good. Charge, we've got 0, goes to -1, +1, +0. So that's allowed. That's also allowed. Lepton number, we've got 0, goes to 1. Muon, positive muon is an anti-particle. It's an anti-lepton. And an anti-electron neutrino is also an anti-lepton. So we can see here we went from 0 to -1. So that is not allowed. Again, strangeness we'll look at. That's fine because none of them are strange. So we know that this is not allowed, as lepton number is not conserved. So just one of those lines not conserved means the whole interaction is not allowed. So lepton number not conserved, this one not allowed. Okay, another way you might see these questions is identify particle X. So we've got to somehow figure out what particle X is. So again, we do the same thing. We figure out its quantum numbers, and from there we can figure out what particle it is. So this is a baryon number of 0 + 1 goes to 0 + 1. Positron, not a baryon. Anti-electron neutrino, not a baryon. Proton is, so therefore this must be. Lepton number, well, that's -1 plus 0, and that is also -1, so that must be 0. It's a baryon. We've already established that, so we would have been pretty confident that it's not a lepton. Charge, well, neutrino is 0 + 1 for the proton, goes to +1 for the positron, must be then +0. So we know now it's a baryon, and we know it is neutral. Okay, let's just check strangeness. Strangeness are all 0 here. None of these are strange particles. So we know it's not strange. So it's a not strange baryon. Well, what not strange baryons do we know that are neutral? It is, therefore, a neutron. So particle X must be a neutron. Otherwise, this wouldn't work. Okay, and the last one, we might be given something like this and asked to determine what the lambda zeros quark structure is. So we might have to figure out a quark structure from something like this. Okay, again, we're going to do that by looking at our quantum numbers. So baryon number, well, a pion is a meson, so 0, plus our proton is a baryon, goes to kaon, is a meson, so 0. So that means we must have a baryon. So we know it's 3 quarks, because a baryon, remember, is 3 quarks. We can do lepton number, but none of these are leptons, and we already know it's a baryon. Charge, always important. We've got -1 + 1 goes to 0 + 0. So we know it's got 0 charge. So when we add our quarks up, we've got to think about that. Okay, so it's 0 charge. And now strangeness, we've got our pion is 0, proton is 0. We go to our kaon, which is a -1 strangeness. Sorry, a +1 strangeness for the kaon. K0 is a +1 strangeness. So therefore, this must have a strangeness of -1, because this is not a weak decay. This is a strong interaction. There's no leptons, and it's not a decay. It's not one particle turning into an array of other particles. So this strangeness has to be conserved in this interaction. So we know it's 3 quarks, and we know it has a strange quark, and we need to get to 0 charge. Well, our quarks, remember, were up, down, and strange. Our charges were +2/3, -1/3, and -1/3. And our strangeness was 0, 0, and -1. So therefore, it must have a strange quark because it's got a strangeness of -1. And then now I've got to get to 0 charge. And the only way to get to 0 charge would be to have a down and an up. So it must be strange, down, up. And it doesn't matter what order we write those. We could write up, down, strange. We could write strange, down, up. Whatever order, doesn't matter. It's 3 quarks, and those must be the 3 quarks it is. So that's exactly the type of question you will get on your A-level paper if you get a question about interactions, either proving it can or can not happen, finding out what the missing particle is, or finding out the quark structure of one of these unknown particles like the lambda particle. Hopefully that was helpful. We'll go back to that sort of overriding sheet of particle physics. That's the kind of thing we want all of our notes to end up like this. That If you learn that sheet, that's everything you need to know about particle physics. For A-level, we'll look more in depth at the strong interaction in the video linked here, because that is one force where we do need to know a lot more about it, and we can get 3-mark answers on that. That's a pretty short video, just covering the strong interaction. We'll also look at specific charge, and then we'll start looking at quantum phenomena, which are really interesting, but often they're long answer questions. People don't like long answer questions, and there's basically a very specific way we can answer those. So make sure you subscribe to the channel to get all the updates, and we'll be working through A-level physics in this playlist.